So let's do an example of just how to draw a free body diagram for a rock that's suspended by strings, but it's suspended in this manner. Okay, so we can always see that there's going to be a force down due to gravity. We're assuming we're in a gravitational field. And now there's two strings, and each one has its own tension. There's string 2, which is pulling to the side, and there's string 1, which is pulling up towards the ceiling but at an angle. Notice how the direction of the string is the same as the direction of the tension, or the force due to the tension of the string in each case. So even though we draw our free body diagram where as if all the forces are coming out of the center of mass of the object, in actuality when we do our addition forces, we know we have to add our forces head to tail. So when we add our forces head to tail, if they're all equal to 0, because the acceleration is equal to 0, then we know that all of these forces added together, in this case it's 3, must basically circle back around. Really what this is saying, these are all vectors. This force is a vector, this force is a vector, this tension is a vector, and this tension is a vector. What we really want to say is that the force in the y direction equals 0, and the force in the x direction equals 0. So the force in the y direction is equal to negative mg from the force due to gravity, and it's equal to plus the y component of tension 1. For the x direction, we have the force due to string 2, which is negative if I make my normal coordinate axis where x pointing to the right is positive and y pointing up is positive. And then if we add that to the tension from string 1 in the x direction, those also equal 0. So you can see pulling these out into the component form is much simpler, I think, than even looking at a picture like this, which can be a little confusing. All this is saying is that it's just vector addition. You can add all these vectors together. Because it adds to 0, they must loop around. Oh, that would be nice if I didn't do that, but I guess I did. All right, so what this is saying is forces in both the x and y direction sum to 0. And we know this because the stone is not accelerating in either the x or the y direction. All right, let's do another example. Again, we have the rock or the stone is being held up by two strings, but now these two strings are pointing in different directions than we saw in the previous one. Okay, we can draw our force body diagram or free body diagram. We have the force due to gravity pulling down, and we have a tension pulling to the right due to one string and a tension pulling to the left due to the other string. We can do the same thing again, where we can draw them head to tail and show that they must sum to 0, and that's equivalent to saying that the sum of the forces is equal to 0, because that's equal to the MA. And again, I'm going to add these little vector signs over top of all of these. In all of these cases, we know that the forces in the x direction are 0 and the forces in the y direction are 0 because we're not accelerating in either direction. So what we can write is that the sum of the forces in the x direction, which is equal to minus mg plus t1y plus t2y, all sum to 0. This is one equation that we can solve. And we can say the sum of the forces in the, that was supposed to be y, in the x direction are equal to, now in the x direction there's no component due to gravity, but there are components due to t1 and t2. You can say t1x plus negative t1 t2x. And that all sums to 0. And that makes sense. You can see that the x component for T2 and the x component for T1 appear to be equal and opposite in these diagrams, these free body diagrams that we've put together.